All right, I think we are live. Good to see everybody. Um, Today we are, let me actually mute my notifications here. Today we are joined by two guests, Michael, who is the engineering manager of the what we call the interoperability team. So that's the Avalanche bridge plus a bunch of the stuff we're working on with teleporters, which he'll go into a bit more later. And then Gyuho, who has been working on the consensus and on the Rust side to talk about Avalanche-rs. Stephen, we had a release yesterday. So if you want to kick us off with that, I'll share my screen here.
Yeah, so this was a little bit of a longer release schedule, especially than we were used to with the fast DB migration releases. But the big namesake of this release is that we finally added pull gossip into our like P2P transaction issuance flow. So what that means is that if people remember the conversation that Josh had, I think either on the last call or maybe one prior, that rather than just quickly disseminating information to the network via push gossip, it also guarantees that nodes will efficiently always hear about it. So essentially, push gossip is really good for getting the information out quickly, but not good at reliably broadcasting it. And then pull gossip is very good at basically making sure that it is reliably heard by everyone. So mixing these two mechanisms together with push pull gossip is a pretty standard practice around like gossip networks to make sure that you have both fast dissemination and everyone in the network hears about it. So we saw like some really long times for transaction inclusion around this, and so we decided to finally kind of bite the bullet and introduce this. In doing so, we did it in a very modular way, so we can kind of plug it in for almost any VM. I think the HyperSDK does a little bit more targeted work with gossiping directly to proposers to try to further save on bandwidth. But for traditional networks, this is a really efficient and performant way to actually get the transactions out. So really excited to see this. As more nodes in the network upgrade, they will further support this, and we'll kind of see the full network passing around these transactions. But yeah, I see you're unmuting, Patrick. I don't know if you have a comment.
Yeah, I was just going to say, people were like, all right, pull base, what does that actually mean, or like what's being exchanged? So to keep it simple, the way that this works is validators will iterate over their mempool periodically and generate a Bloom filter of the transactions that they currently have seen or have in that mempool. They will then send that Bloom filter or gossip it out to a random set of peers, other validators. Those validators will then basically take that Bloom filter, iterate over their mempool, and see, is there anything in this Bloom filter that I have that is not in this Bloom filter that I have that they don't, and then they will send it back to the validator that actually gossiped that original Bloom filter. And then obviously Bloom filters over time fill up. And so you have to refresh them periodically. So once it reaches a certain error rate, the validator will reset its Bloom filter. So that means that every time it sends a message, it doesn't have to like do a full iteration. That's a very periodic mechanism, and then it's all in memory, so it also is pretty quick. Steven didn't want us to use cuckoo filters, so we had to stick with Bloom filters. Cuckoo filters would let you remove objects from the Bloom filter, so you wouldn't have to refresh it, but there's some concern in his mind that works.
It's not a question of whether it works or not. Like, cuckoo filters are definitely well researched. They're just jank. Like, cuckoo filters have not received a large amount of adoption in the filter game, I would say, for various
in the
reasons.
large and growing filter game, yeah. Yeah, so I think so. This is something, as Stephen also mentioned, that has been implemented actually as part of the P2P SDK. So this is a trend you'll see from us as well, as we're trying to better modularize the different virtual machine components for better reuse within the VMs maintained within Avalanche Go, but also for anybody. So just to give you some comparison, right? Like prior to this, you would have to implement entirely your own gossip, which is the way the P chain works, the X chain works, and the HyperSDK works. But by better making more reusable components, it can be more effective to maintain and test a smaller set of things. And so we're trying to take that approach with the Merkle DB, which will be used across a number of different virtual machines, with state sync, which will be used across a number of different virtual machines, with databases, just trying to extend that as much as we can to make everything easier to manage. Aaron, is there anything you'd like to add to this? Steve and I are talking like we did it. You actually helped integrate it. So.
Yeah, I mean, that's why this PR is actually closed, because this PR started out on Corey. So this was the best description that Josh came up with, which is really, if you want to learn more details about it, this has a great description really talking about the motivation, which was that we were seeing, transactions typically reach whoever's going to build a block very quickly. But the one thing that it didn't do was make sure that the P99 time was also very good. And so what can happen is, as you sort of push gossip transactions to the network, they only push gossip again if they have not already seen that transaction. So you only push gossip if you're learning about it for the first time. And the problem with this is that as you reach, let's say 80% of the network has received the transaction, it becomes less and less likely that when you receive it, you'll be receiving for the first time. And that results in this bad P99 time. Whereas for that last 20%, who maybe haven't heard of a single transaction, if they're just pulling randomly across the network, as long as anybody that they pull has seen this transaction, they'll eventually get it. So, you might have some possibility that, it might take 5 seconds instead of 2 seconds, but you'll still get it very quickly, and you won't have nearly as bad of a P99 time. And I think we'll probably add as well at some point direct to validator or direct to the next proposer gossip as well. And this was also, since it started out in Corey, this was, I think, the first VM peer-to-peer SDK component that we actually moved back into Avalanche-Go, as we just ended up seeing that it would be easier to integrate it there, especially as, this PR started out as, I think, 1,500 lines of code or so. And we ended up breaking it up into much smaller PRs, going to Avalanche-Go, breaking it out into first the P2P SDK, then the Bloom filter component, then integrating just generally using the P2P SDK within Corey, and finally actually integrating the Bloom filter gossip component, which was really nice. It ended up that the PRs on the Corey side ended up being really small, which is always something that I like. And Steven, we always go back and forth on whether or not useful things should be in Corey for the first time or put them into Avalanche-Go. And my bias is always to put them in Avalanche-Go, so it's simpler inside of Corey. So this one I won out on.
Yeah, and I think keep watching out for, I think we'll probably transition more of the existing mempool gossip logic and other networking interactions to use the SDK. So I think one of the big areas here is the push gossip that is done by the C chain by Corey is still done using the previous network handlers. And watch out for us to transition that over to the new SDK as well, and then probably integrate this same mechanism into the X chain and P chain. So.
Yeah.
There's a quick question here from someone named Goss. How frequent does the Bloom filter computation take place on average? I know it's an account-based thing rather than a time-based thing. Do you guys know what that count is?
Yeah, so I think that we end up refreshing the Bloom filter if the error rate goes above, I want to say 5%. And so that means that I would have to look up the exact numbers, but it's a function of what the throughput is of the chain. So say every 10,000 transactions or so, it'll refresh. So that's kind of how that works. So it's not an explicit timer based mechanism, but more like the number of elements that we've added. So yeah.
Yeah, so as transactions are getting added to the mempool, we'll actively add them to the Bloom filter. So it's not like we're doing this large computation all at once, except for every so often when we hit that error rate, we'll refresh the Bloom filter so that we don't have a stale Bloom filter with a high error rate. Would have to do the math to get the exact frequency with a expected throughput of transactions.
One of the big things that we had to worry about here was making sure that people couldn't spam Bloom filters as well. So there's a whole bunch of throttling logic and various work that had to go into the SDK to kind of support this new pull-based mechanism, which is one of the big reasons why we actually didn't introduce any pull-based mechanisms early on. Is just because push-based mechanisms are very easy to rate limit, whereas pull-based mechanisms are slightly more annoying to rate limit. So I'm sure people will have fun digging into that area of the code for sure.
You're interested in the contents of the mempool at any given point in time, poll gossip may be of significant interest to you. So I'm sure this will be dug into a lot.
Anyways, I think we've probably beaten this this topic to death. There are a couple other things that got into this Avalanche Go release that were pretty interesting. So the first one I want to shout out is the Merkle DB splitting of the intermediate nodes and the value nodes. So the reason I'm really excited about this is for two reasons. One is for range proof and change proof generation, which happens when you're serving nodes they're trying to state sync. We won't have to iterate over any intermediate nodes anymore, which means that you can essentially much more efficiently generate your range proof and change proofs off of the current state. So that alone is a really cool change. But what that also lets us do is actually compress the keys of the nodes. So previously, the key was actually like twice as large as you actually inserted it because we had to break it into half bytes or nibbles. And so if you inserted a key that was like 10 bytes long, then it was actually stored as a 20 byte key. Whereas now what ends up getting stored is actually a key of either the equal length or one more byte. And so we're able to compress these keys and save a very non-trivial amount of state on the key space side, which is really cool. So yeah, I think that's really interesting. I know that Patrick, you really liked this PR as well for being able to split the intermediate cache and the value cache out because
well, I mean, so this is an interesting one because typically in these like Merkle tri based structures, like the intermediate nodes are much more temporal, maybe we'll say, than the value nodes, and so they change much more frequently. And a lot of networks that have large Merkle trees very rarely, if ever, actually write the intermediate nodes to disk because there's so much additional overhead to keep those up to date. At least with it just makes everything worse, right? You have way more keys in the database, so you may be doing more compacting if you're using like an LSM based structure, and then it's also a lot more data, and then every block you're deleting and rewriting thousands of them. So like if you can put them in memory, that's great. Previously it required everything to be in the same cache, which was suboptimal because usually within a cache you want whatever is being stored there to have the same like access pattern. Otherwise, like you may like pump in a bunch of intermediate nodes and then evict a bunch of value nodes that may be larger, more useful for like what you need. So like it was not possible yet, but now this is in, and it also is size based, which is huge because for networks where you don't actually know the size of the value that's going in, storing just based on item count can be potentially a memory issue. So yeah, the HyperSDK updated this right away.
And it passed all the correctness tests on the HyperSDK too. So huge right there, huge. Anyways, and then I think that the last thing I wanted to shout out for Cortina 10 was the Proposer VM header deletion stuff. So this finally landed in here, and I think that this was the last thing on the Avalanche Go side that was blocking the HyperSDK devnets. So, or at least until Patrick comes up with something else. So I'm really excited to get this in. This is not technically supported. This is not technically supported on any of the primary network chains, but for any subnet operator, you can specify in the subnet config to essentially delete old Proposer VM blocks. So this is especially useful for someone running a hyper VM because if you're really hammering throughput through this chain, just the actual block data can actually become extremely massive. So you can kind of do dynamic pricing on like state creation and state size, but you don't want to like always be allocating these blocks to your to your database. Now, if you do this, you are essentially removing the ability to perform a full sync from the network. So it is definitely important that pretty much any blockchain has a record, at least, even if you don't necessarily support it in a decentralized P2P way to perform a historical sync. You definitely want to have that data around somewhere. But yeah, this is a really kind of cool way to unblock some of the more high performance VMs. So yeah.
Yeah, I finally fixed the README, by the way, for the HyperSDK, which did the math. So for 10 megabytes per second, that's 864 gigs per day. It was nuts. And then for a whole year, that's like 300 terabytes or so. So you can imagine if you want to operate at high throughput and everyone's storing that data, that's a lot of data to keep on disk and continue to maintain, especially because a lot of these databases, as I mentioned before, get less effective the larger that they get. So it actually gets like exponentially worse as you add more stuff to the database. So you want to keep things as limited as possible. So the HyperSDK, for example, just keeps the last 768 blocks, and that's it. And so that is enough for it to like restart successfully. If there's like, if it shuts down, comes back online. But that's fully tunable. So you can tune that if you want a larger window, but for like a ultra high throughput case with a minimum block time of like, let's say 200 milliseconds or something like that, you may want to set a time window that you prefer to have. But big improvement because I was quickly exhausting disks when I was testing out the HyperSDK. So this solves that problem.
This was the middle ground between doing the microblock strategy versus
Yeah, if you remember us talking about that a few weeks ago, yeah, this was the compromise, which I'm very fine with. The microblock stuff was cool, but extremely complicated. All right. I think this was the major points here. I think there's a lot of other, there's actually like 20 MerkleDB related changes in this release. So clearly we are working on that, and we'll start hopefully auditing it soon for inclusion in production and usage. And then, we'll cover some of the other stuff coming there next call related to changing the branching factor, which is a big thing that's been discussed. So I'll take note of that actually as well. Cool. So next, go ahead.
I was just gonna say, yeah, we're getting really close to having the disk layout and theoretical hash structure to be at a point that it's solidified and moving into like a kind of performance / correctness exclusively mode. So couple last few things, one of them being like a root node calculation and things like that. But yeah, we're really close on the MerkleDB side to kind of say that it's feature frozen, I would say. So I'm excited about
that. So next we'll talk about Avalanche-rs. So Gyuho, our resident Rust Maxi, you can go introduce what you've been working on.
Yeah, so actually been working on this over a year. So a year back, the goal was like to create a subnet using Rust, which back then like seemed easy looking at how Go was doing. But it turns out like we had to like build everything from scratch. So for instance, to issue a p-chain transaction, you need Avalanche specific like transaction codec, which Stephen can talk more about. And then you also need Avalanche specific like ID, like a type, like a format, and things like staking, like a key generations in Rust. Plus, like we wanted to make sure every Rust code, like we write, like fully conformant and then fully like compatible with our Go code. So for that, like we also had to build like a network runner SDK in Rust for our like end-to-end testing. So like it took us a while, but pretty happy like where we are today. So who is using this, and then what do we have in this repo? So yeah, we have our first, like we have our Avalanche types at the top level, like a primitive types that we just mentioned. And then we have a consensus like implementation in Rust. It's like we have every single unit test, like a translated from Go code. And then we have our networking, like to send some P2P messages. And then also we have a RPC chain, like a trade implementation, then you can use to build your own, like a custom VM in Rust. And then, yeah, this repo is called like Avalanche-rs, but it's not on like a full node implementation yet. So you can think of this like a more of like a set of building blocks. So everything Rust in Avalanche ecosystem. So yeah, who is using this? So as of today, we have our Avalanche ops using this to set up DevNet. And then we also built gateway layer, like using this to process like a guest list transactions. And then we're also using this for distributed like load testing. And then we have a Ash, like a command line interface from the community. Yeah, they can even do like a multi-cloud, like a DevNet deployment, which is pretty cool. So yeah, a couple of like lessons here, like for over a year of development. Like I think we came to appreciate the simplicity of Go code, like as like a translating like a Stephens, like a consensus Go code into Rust was a bit of challenge. Like you can tell if you look at our consensus code in Rust. And then also really appreciate like a great Rust ecosystems, like around cryptography libraries, and then like which is mainly driven by the Ethereum community, like which also like a big help. So yeah, please check it out. Like we are looking to get more contributors. Yep.
I had no idea Ash used this as well, their CLI.
Yeah, so the one of the founder is the like a big contributor to this repo. Yeah.
Ah, very cool. Yeah, so on the Rust side, we as Guho mentioned, there is no full Avalanche node completed. And that's not an immediate goal for this repository. The immediate goal more so is unblock subnet building with Rust. So Movement, for example, is using some of this code for implementing their subnet. But for consensus research, I think at some point, it'll be important to build a Rust-based client. And I hope, someone in the community may take up that mantle using a bunch of these different types. Definitely not for the faint of heart, for sure, to get that off the ground. But, we have been getting deeper and deeper into Rust with the HyperSDK programs as well, which are also all, at least the happy path is all Rust-based. So we could definitely probably also be using this in the future to actually interact with different Avalanche types within a contract. So yeah, very cool. Anything Stephen or Aaron you guys want to add? Or Michael, I guess? I don't know how much Rust you write.
I'm just, I'm looking forward to getting to a point where we can really fuzz the consensus engines amongst each other. You don't actually necessarily need to fully implement the VMs in order to kind of do this, which would be a really interesting kind of like network simulation for us to do. But yeah, I haven't really looked as much into the consensus code here as I probably should. But it's super interesting that we're kind of so far along with that here. And I think we probably have a couple consensus like improvements coming down the pipe, so it should be interesting to kind of play around with those in both Avalanche Go and Avalanche-rs. So those are my thoughts. I think it's super cool.
Yeah, I'm super excited to see more Rust development. I know it seems like everybody that we've hired in the past 6 months or so is like a passionate Rust supporter that only wants to do Rust development, which is crazy. I've never seen this much passion for a programming language, and I'm on chapter 14 of the Rust introduction book, which I come back to like once a month or so. But yeah, super excited to see it come to life, and very excited for a potential consensus client at some point in the future.
Yeah, I think excited to see where this goes, and I still need to learn Rust, so that's coming around as it does. Cool. So thanks, Guho, for stopping by and continuing to maintain this. Look forward to seeing more contributors pick it up. So yeah, with that, next we will go to Michael to talk about everything Teleporter.
Yep. Hey, everyone. Thanks for having me on, Patrick. So a few weeks back, we announced the open sourcing of a couple different repositories related to the Avalanche interoperability team. And those are Teleporter and the AWM Relayer. So I'm going to go into a bit of detail about what each of those are, what they do, and then this also awesome demo that Connor Chevley put together to help us show it to the world. So Teleporter itself is a cross-chain EVM asynchronous smart contract invocation solution. So it allows any smart contract within the context of an Avalanche EVM subnet to call another Avalanche EVM subnet and invoke arbitrary contract code on that destination chain. That is super powerful because it really enables building any type of cross EVM application, bridges, oracles. You can really go wild with all the possible use cases. So just a bit about how it works. So it's built on top of Avalanche Warp messaging, which I think Stephen, Aaron, and Patrick have gone into to a good extent on previous sessions here. So I'll try to keep it just Teleporter specific rather than going into Warp. I'm sure Aaron's happy to expand on any of those details. So with Warp in the subnet EVM, you can basically get authenticated messages from one chain to the other. Teleporter builds on top of that by enforcing a specific message format that provides some properties that could be useful for developing cross-chain applications. Some of those properties are message IDs to, for instance, provide replay protection, ensuring that a message can't be delivered multiple times, which Warp itself doesn't provide. There are also fields for message fees, so you can incentivize someone to deliver your message for you to the destination. And then also it uses low-level EVM call to actually execute the message payloads within the context of the EVM, rather than just delivering the bytes to be stored. I guess another cool detail that I can go into is that it's deployed using Nix method, which I think was either Steven or Aaron's idea originally. So definitely credit to them for suggesting it. But this allows the Teleporter contract to be deployed to the same address on every EVM chain. It also allows that contract to check that the sender of any message it's receiving matches its own contract address. And just by ensuring that it was sent by the same contract address that it's now being received on the destination chain, it knows that that message was generated by the same contract bytecode. So it must have the same format, and it can interpret those fields to provide these properties of replay protection, message execution, relayer incentivization, etc. So I think that's a cool technical detail. Happy to go into more detail on. The other repo we open source at the same time, though, is the AWM Relayer, which is a service that you can run, anyone can run to relay and deliver these Warp messages across any chain. Right now, it's just set up or implemented for EVM. So just a little bit about the relayer. On a theoretic level, anyone can relay their own Warp message. And I think that's a really important property of this protocol, that there's no trusted intermediaries. Anyone can relay their own messages by themselves. In order to relay a message, you need to aggregate the BLS signatures of the origin subnets validators. Hi, Stephen. And then put that message along with the signature in a transaction that gets sent to the destination chain. So that's possible for anyone to do by themselves, and that's a really important property of the protocol. But there's any number of reasons that the person sending the message may not be able to or want to actually relay the message themselves. So one, it is a bit more clunky of a UX because you have to then send two transactions, one on the source chain, one on the destination chain, in order for that message to be sent and then subsequently received. And two, you might not have the token to pay for gas or transaction fee costs on the destination chain. If you, for instance, are moving to a new chain for the first time, you don't have the native token of that chain, you can't send your first transaction to swap into that token and be able to send subsequent transactions. So the AWM relayer is an application that can be run as a service to relay teleporter messages and more generally any warp message. Like I said, it was initially just implemented for teleporter, and we're planning on extending it as more messaging protocols come about on top of warp. And lastly, just want to reiterate that really any cross-chain application could be built on top of warp, and we are super excited to see what the community will build, what the possible use cases are, and we're eager to get feedback to see how we can improve on the interfaces and functionality provided by Teleporter and by Warp for that matter, prior to its launch on Mainnet. The demo application that we put together is at ohmywarp.com. Patrick had that up earlier. It is an ERC20 bridge across some Warp-enabled testnet subnets, and I definitely recommend checking it out if you're interested in kind of diving into Teleporter. It's a great way of interacting with it. Then you can see the transactions, how they're constructed, what methods they're calling, and enter the contracts from that point. So yeah, happy to answer any questions. Also, a huge shout out to the 3 other people on this call, Stephen, Aaron, and Patrick, for all of the work that they put in on the platform side to enable Teleporter to be possible.
Yeah, so the quick context here too, just to put you in, orient you in space, is I think Stephen, what was the first day warp message was sent? It was like the 22nd, I think, of December last year.
Yeah, it was in December. Yeah.
Yeah, so the first warp message sent on mainnet was in December, but that really was just the warp primitive. So there was an example VM that was built called the XS VM that was Stephen again. And what this allowed us to do is just test out and make sure the primitive, like, a source subnet could sign a BLS message, the signatures could be aggregated, and then that message could then be verified on the destination subnet, and it all worked. However, that was only the first step on this journey. So, if I asked you how many people were using the XSVM, you'd say 0. Well, really 1, Stephen. I didn't even know how to run it. Therein lies the problem, right? Everyone that uses Avalanche, or the significant majority of people, use some variant of the EVM. And so it was really important from that moment to find a way to support Warp within the EVM. Now, for the reasons that Michael mentioned, it isn't necessarily a straightforward thing. So, Warp doesn't provide a lot. It lets you push bytes from one place to another with a signature around it. So if you want to make sure it fits within the EVM call data type, make sure it has replay protection, make sure it actually is usable and safe from a contract, there's actually a lot of extra work that needs to be done. And so we've been working on this for the past 9 months or so. And they're finally now at a place where we've had it audited twice, one by Least Authority, one by Lewis, actually from Trader Joe. And then we're going to do one more audit with Open Zeppelin on this in the coming weeks. And then are working on also doing an internal red team exercise led by Aaron to try and find any bugs with it. It's probably at least in my opinion, probably Aaron's opinion too, one of the biggest features we've ever shipped on the network. And I think it will unlock a huge amount of usability within Avalanche, which is solving the central problem, which is subnets right now are isolated. So this will let subnets talk to each other and will let subnets pull information from the primary network, whether that be a Vox token, whether that be some state, whatever it is, it will make everything feel much more connected. So that's my brief orientation. If you haven't tried the demo, check it out. It's really awesome. Anything, Stephen or Aaron, you want to add?
Yeah, I think the really cool thing about this and this teleporter demo that I highly recommend you check out at ohmywarp.com. The really cool thing about it is just the fact that you can now, or you will be able to launch your own blockchain and then immediately get direct access to all of the liquidity that exists on the C chain, which is one of the most difficult things when it comes to bootstrapping a new network. And we're really trying to solve that with this native communication protocol, where people will be able to have all of that liquidity that exists on the C chain very natively and very easily move it directly over to their new blockchain without actually interacting with any sort of gatekeepers. There will be, minimum integration points. You'll have to set up your own relayers, but it'll be all fully open source software that you can mod as you want, and just get direct access to all of that liquidity. So I think that'll be a really cool impact of this, and hopefully unlock a lot of new use cases and a lot more excitement from the community about, what the possibilities are and how to actually use Avalanche subnets.
Yeah, I know there's oftentimes a lot of concern around like bridge operators between different networks. And I'm just really excited that we can kind of finally push this solution to really remove the concern around any kind of bridge keys being like hacked and taken. Like, there's no like special group of people that are authenticating these messages, right? It's the actual validator set. So you really you get to cut out this whole area of security concerns that traditionally come in with these kind of like cross network messaging protocols. And so yeah, I'm really excited for kind of the wider like subnet ecosystem to start kind of like picking this up and kind of further decentralizing their communications between each other. So I think that's that's definitely my most like excited part about this. So
yeah, I think the really cool thing about this, people have had their questions about what the security properties of Warp are, and I think the best way to describe it is that there is a paper, or a systemization of knowledge paper on all cross-chain communication protocols, where I think the reality is you can probably read 3 sentences of it and pretty much get the picture, which is that for cross-chain communication protocol to exist, you always have to have some sort of trusted third party to establish, what happened on chain A to chain B. And the question is just, what do you use as that? So a ton of protocols will use some sort of a multi-sig. These have been, hacked for billions of dollars going back the past few years. And the best that you can really get is what Warp is going to offer you, which is the same security as the minimum between those 2 points, which is to say that Warp is going to have a signature of, a threshold of the validator set of subnet A to be verified by subnet B. And it's essentially replacing this dependency on some arbitrary third party with relying on the P chain to serve as the root of trust for what the validator set of that subnet is. And the point of doing this is really that if you have a threshold of the validator set that's signing a message, then if that threshold of validator sets were compromised, they would also be already compromising that network anyways. So Warp communication, the Warp primitive, really gives you the best possible security properties that you can get for 2 subnets talking to each other that you can possibly have. So that's the really nice property about this.
And just to build on top of that, I think this is also just the very beginning, as Stephen was kind of calling out, of Warp being integrated into the subnet ecosystem at large, and super excited to see where it goes. Teleporter is just one possible protocol built on top of Warp. And it's really designed for point-to-point contract invocation, but there's so many more possible use cases that we're excited to see what the community will introduce and build, and we can help facilitate.
There's also one comment from Gauss. Gauss, I'm very glad that you brought this up of then we can finally, actually I won't. But this actually also allows you to use Warp as a primitive to integrate with layer 0. The way that layer 0 is built is they have this block hash oracle, which is really the one dependency to provide, that trusted third party to say what happened on another chain, and then everything gets proved out based off of that block hash. So you can actually also integrate Warp directly into layer 0 using this block hash payload that's up here, where what you would do is you would have an implementation of that block hash oracle that uses Warp to actually verify the block hash was signed by a threshold of the subnet validator set. And then you would be able to use all of the existing SDK tooling from layer 0. But instead of using the trust that goes with that, you would actually be able to use Warp as the security properties of Warp along with the SDK offered by layer 0, which would be really cool as well.
Yeah, it's I pulled up these payloads because I think it's useful to indicate like what is actually being sent over the wire here. And this is a payload that is understood or will be understood by the different EVMs within whether that be the C chain or different subnet EVMs. And so we're currently discussing how exactly to hook up HyperSDK to this as well. And it's important probably that it'll have to support something kind of like this to be able to talk to the C chain at least, because it'll be important then to actually get like a Vox to pay fees maybe into the HyperSDK, which sounds really nice. So we're going to keep playing around with this primitive and make sure that it works well for everything. And then there was one question for Michael, which is, when do you think subnets can fully use Warp or Teleporter?
Well, I don't think
I see one of the question here was 5 years, so hopefully we beat that.
Well, considering we're coming up on, or is today the 3-year mainnet anniversary? Is it tomorrow? I'd certainly hope so.
It's Friday, 22nd.
22nd. I thought it was the 21st.
Was it? I think it's, I don't know.
Depends on the time zone.
Yeah. But given we've only been 3 years since mainnet, I'd certainly hope it wouldn't be 5 years. I think we're talking months at this point. The first thing that needs to happen is a required network upgrade to actually enable Warp, which is implemented as a precompile within the EVM on the C chain or any subnets, mainnet subnets that want to support Warp. Once that happens, we're hoping to be ready to move forward with the teleporter contract and AWM relayer. Anyone can set up their own relayer, but we can offer that as a service also soon thereafter. So it's been a long time coming, and I think now that it's really the ball's really in motion on it, we should hopefully see activity pick up in the coming months.
Yeah, I think I'm extremely excited. I think, we'll probably integrate it in some form into core and like a bunch of other stuff to really make it feel seamless here. But it's, obvious it's been an ask for a long time. So we'll be exciting to see this get off the ground.
Absolutely.
Cool. Well, thanks, Michael. We'll stay tuned on your progress here, and we'll probably bring you back on when we get closer to maybe the next network upgrade, which will actually activate it itself. So,
looking forward to it.
Thanks, Michael. Cool. So yeah, next thing I think we have 12 minutes left, but we're so on a roll, we might as well continue, is talking a bit about the ArchiveBD. So this is a project that's being worked on by someone on our team. And this is a really important thing for a lot of reasons for what people have asked for. And so maybe Aaron or Steven, you want to take the lead on explaining what this actually is?
Sure. Or I don't know. All right. Yeah, so the EVM or a lot of projects that are built on top of the EVM require full archive node support. And this means that, they need to be able to access the full state at any given height from height 0 to whatever the current height is. And this requirement is currently met in our EVM implementations, which use a fork of Go Ethereum using a hash-based Merkle tree. And so what this means is that we write all of the intermediate tri nodes, which Patrick was mentioning earlier in the call, can be a large number of nodes that are rolling over very frequently and ends up being a large amount of data to disk in order to serve that Merkle tree at any given height along the way. And this allows you to look up the state at any given block throughout history. And so the ArchiveBD is looking to implement a more efficient version of this, where instead of having the full hash-based Merkle tree, we'll actually use a diff-based approach to write only the diffs that were applied at a given height so that we can look up what the state was at that given point in time. And so this approach is motivated by the work that Aragon has done to build more efficient ArchiveDBs, as well as the work that Reth has done. And they've put together both projects have put together great documentation as well that motivated us to go ahead and try this approach. So that if you want to build a Merkle DB, which we're also building with our own Merkle DB that only stores the current state, or stores a smaller, or doesn't necessarily store the entire full historical state in a hash-based Merkle tree, you can use the ArchiveDB in order to record all of the diffs that occurred at any given height along the way, and use that in order to look up all of the changes, all of the key value pairs that exist at any given height. So this is a very, very important requirement if we are going to use MerkleDB inside of the EVM, which is a sort of research project that we want to try out to use our own Merkle database implementation in order to also support archive modes that you would be able to actually view the full key value pairs at any given point in time. And the reason that this is important, one example of why this dependency might exist is if you wanted to look up a balance at a given point in time for your application, that is actually going to be served by using the ETH call RPC endpoint. And so what you're actually going to do is say, hey, perform this transaction, which might be a read-only operation at this given height. And it will perform a transaction where it calls a smart contract saying, hey, what's the balance of this address at this point in time? And that'll actually depend on the state at that point in time. So if you want to switch on the node to make it a more efficient implementation that only stores the current state, you need to have some alternative way to store the state throughout history. And the really nice thing about the ArchiveDB is the way that it's built is you actually have O of 1 lookups of any state throughout history. Whereas with the hash-based Merkle tree, using the Merkle tree that's fully on disk at any given point, you will actually have an O of login operation to perform those historical reads, which will have significantly slower performance than what's offered by operating at tip. Where at tip, we actually have an O of 1 snapshot or a flat key value version of the MerkleDB, so we can actually look up those key value pairs in an O of 1 operation instead of traversing through the entire Merkle tree. And the really nice part about the ArchiveDB is that we actually very carefully place the key structure of the ArchiveDB by basically setting the key to be, you can scroll down. Actually, I don't know if there's a great place to look at it here, but what you basically do
is there that separate PR actually that hasn't been merged yet, or has that been merged in?
That's been merged in. That's the internal representation for the DB key. It might be a good place to look. But basically what we do is we take the key that you want to read, the key that you're applying a diff for, and we'll actually put that key in the database and put a suffix of the height that you're applying the diff, so that if you ever want to read the value of that key, what you do is you actually perform a get operation where you take the key that you want to read and then add the suffix of the height that you want to read, and then iterate forward from there. And so you're guaranteed, if we are applying all of those put operations with the inverse of the height, that when you read that, the first height that you read, or the first height that you read with that key as the prefix, will actually be the most recent change that was made to that key. So if there's nothing there, it will read an empty value, and you'll see, okay, this is empty, and you'll get database error not found. If there is any change that was applied to make it a non-empty value, then the first thing that iterator will read will be the most recent change. So it'll be the actual sort of the pre-state at that given height. And so you can very quickly read that by just grabbing one of these database iterators and reading only the first value ever. So this makes it so that instead of ever having to iterate or do an O of login operation traversing through the Merkle tree, you'll always have an O of 1 lookup into the historical state, which will result in significantly better performance.
That also means that it's O of 1 writes as well, which is super nice.
That also means that the size of the database will kind of show those like really phenomenally compressed formats that you see on like Aragon and Reth for their archival support. So yeah, this is really designed to kind of dovetail with the MerkleDB and kind of further our push for making SDK components for VMs where, like for the live state, MerkleDB is the way to go. But if you want to support archival, then, we also need to have some form of solution for that, just because people do need it. And so then this is kind of where this comes in. So definitely don't want to claim too much on the research side of the actual DB structure layout. I think this was kind of pioneered by Aragon, but yeah, really kind of excited to see these kind of like more advanced database structures proliferate more throughout the ecosystem. I think Geth is also planning on introducing a similar mechanism for their archival support with path-based storage. So really excited to see kind of the innovations here.
The nice thing with this is it's fully generic though to just the keys, whatever you want to put in there. So it can just be used off the shelf by any virtual machine. It works really well though with the MerkleDB, and we'll make sure that that works nicely. The big change here, or the big trade-off, because you may say like, well, why doesn't everyone has like always just done this? Is that it actually gets really difficult and slow to generate historical proofs of data, because you don't actually have the historical tri structure. So if you were to generate a proof of a certain value at a certain height, you would have to reconstruct somehow the tri representation of that data, which is typically done via like reverse diffs, or like by basically reverse diffs off periodic saving of the tri structure. So if you want to generate a lot of proofs of a historical data, not great. But if you're okay really just accessing the data itself, this is much more efficient.
Also, this isn't super efficient to do any iteration of the state at a given height. That's explicitly not a design goal of this.
Yeah. So I think we're still basically testing the right database to use with this. So because of all the iteration, you may be tempted to use a B-tree implementation like bbolt and Golang, but we've also seen really good performance on other workloads with Pebble. And so we are in the middle of also testing that out to see what the sort of recommended path will be for actual usage. So yeah, anyone else have anything that they want to add? Alrighty. All right. So I am now going to set up the HyperSDK GUI demo, and hope this works because it's a live demo. I set up a staging server here, so if it's dead, we'll come back to it next week. But I am hoping that we are good. So just give me a second to compile this.
Patrick never learns that live demos can go sideways.
I can. So that's why I recorded the unboxing of it. So if you want to check that out, I recommend that, because I waited until like late last night when it was totally quiet so I could record it, then went just a straightforward full demo for 15 minutes or so, talking about how it all works and some of the inspiration for it. But as I pull it up here, I will talk about that. And this will only take a few minutes, I think. I should have this up, so apologize for that.
as much as you might want to close out of Chrome to get the throughput higher, don't. We had the inside joke on that was we had this this demo with a company around the HyperSDK at one point, and Patrick had Chrome open, and Chrome was using all of the resources on his laptop, so HyperSDK was just so slow. And then after we killed Chrome, it's sped up quite a bit. But I think that the numbers that we see now on the HyperSDK put those numbers to shame. But anyways.
All right, so I got the demo here. It is still up, which is great. So right now, there's no activity on the network. I'm just running this basic demo here. But so to give you some context, up until now, to use the HyperSDK, it's involved using some form of a CLI, which for most people, they would never do that. So even though it's basically the optimal way to interact with technology, people seem to believe that a GUI is better. And so I was forced to learn how to build front-end code and wrote this whole thing over the last few weeks to create a much more cohesive experience for interacting with the HyperSDK. And at first it was a little shaky. I wasn't not confident that it would get to this point, but I pushed through and implemented a full wallet for the token VM. And it includes an explorer, a faucet, token minting, token transferring, token trading, and a feed. The feed is like a social feed that you pay with micropayments. Steven's laughing because, like, with everything I do, I just go overkill. Like, this is definitely not required to get to this point, but it turned into a passion project. Yeah, I'm going to show you how it works here. And the basic thing I want to call out is this all uses something called Whales, WAILS, which is something I thought was too good to be true, but just actually works, which is an Electron alternative for Golang. So I can take all of the Golang code that we've written for the HyperSDK and basically auto-generate TypeScript function calls and models just directly in it. And that's important because the HyperSDK code is still being actively developed. And so if I had to pause the world, implement everything in TypeScript, and then if I changed the cryptography, like, it would break everything, right? So with this, I don't have that problem at all, which is super nice because anyone that's developing this can still iterate very quickly and then just skim it with React at the end of the day. I also used a component library here. I'm not a designer, so this is just a bunch of open source stuff from actually Ant Financial's React design library.
But look at how smooth the refreshes are. Wow.
Yeah. So, all right. So we'll have some fun here. So the way that this works is there's a few different actions you can take. You can see I added even like this nice little warning. You don't have any funds available, and grayed out all the icons. So you can't even do anything if you don't have any funds. And so first I implemented a proof of work faucet. So the proof of work faucet has automated scaling of difficulty based on how many solutions are actually suggested over a window period. So let's say that someone's spamming the faucet, the difficulty will automatically go up to prevent people from basically taking all the funds. And then if no one is able to solve solutions, it will also automatically decrease, which is super nice. And so I'm just going to request funds here. My computer is now running a proof of work, basically a multi-threaded search for finding a SHA hash that has the first 25 bits as 0. So that took my computer about 8 seconds, and I iterated through 50 million different possible combinations. This difficulty you can tune as much as you want, but the important thing here is I now have funds. And so my funds here, and then my transaction history was the deposit. So now I'm going to go mint a token. We'll create it and call it, what do you guys want the symbol to be? I don't know, we'll call it
Pog.
Pog works. That's what I did in the other demo, but my favorite number is 5, and we'll call this, dev community call. So finalize. You can see the Explorer is now updated with these cool little charts that shows transactions and active accounts, which is pretty cool. So now I'm going to go back to the mint. I don't have any supply yet, so I'm going to mint myself. Oh, wow. Like, look, there's an address book. You can add people to that too, which is super nice. So I'm going to mint myself 100 POG tokens. You can see my supply went up by 100. You can see the transaction history. I created an asset. And I minted it. You can also see the units that were used. So I created a new key here, so I paid a creation fee. And then I'm going to transfer this token, maybe to myself again. I can pick whatever tokens I want. Let's say POG tokens, 1 with memo, like, hi. Then you can see it live updates. The memo here all works. And then you can trade tokens, which is also a really important part of like kind of showcasing what this thing can do. So I'm going to create an order where I'm willing to buy tokens. So basically I want more of the native token, and I'm willing to buy basically 0.001 token per 0.01 POG. And I'm willing to supply, let's say 0.1 POG for this. So I will show an open order and the rate at which I can now exchange these things. So now let's say I wanted to fill my own order. I would open up the order book where I'm trying to go from token to POG. And let's say I wanted to provide, I don't have that much money, so I'm not going to buy too much. I'll send basically 2 token at 0.002, and that'll fill. giving me some of the POG. You can see that the amount remaining went down and the like max trade is available. And then when this price is wrong, I want my money back that I locked up for people to trade against, I can close that order and it will return the funds back to my account and get rid of it. And then lastly, the feed, which is the fun part. I love creating these sort of things, is you can create posts similar to the proof of work mechanism. It's a dynamically scaling difficulty based on micropayment amount. So if there's a bunch of feed posts that go in during a certain period of time, the price will go up. And similarly, if there's nothing, it will go down. So I created a few posts last night where I uploaded some of my favorite XKCD memes, and then it basically, when you post, you can post just a message or a message and a URL. In this case, I posted a URL. Then the wallet will actually like fetch the metadata for that URL and then display it if it exists. And then if you click this, it will open it up in a separate browser. But the cool thing is you can tip people for posting cool stuff. So if you tip someone, you can actually pick whatever token you want to send them. So in this case, POG. I'll give them 1 POG token myself and say like, nice post. Tip. And then it will send that transaction. You can see here the memo. So yeah, I think I'll probably show these as comments at some point, but clearly I got carried away with that. So I'm not going to introduce the comment feature, although you could. So the faucet and the feed thing are fully open source, and they use all the HyperSDK stuff. The wallet is also open source for anyone to extend. And I think this will become my default for showing examples now, because it's much more approachable. And when the DevNet is launched for the HyperSDK, we'll basically produce a Mac application that anyone can download and play with. I think you can also generate Windows as well as Linux applications as well, but I got to figure out how to do that first. So yeah, any questions?
So
Are you a front-end dev now, or?
No, do not confuse me. So I figured this out too. Like, you can make something look very reasonable, but I can assure you that behind the scenes, the code quality for this is not great. So, it's interesting that that's the way that it works, but the code does not look nearly as clean and put together as the interface.
there's going to be some gnarly URL like injection stuff going on here with this Explorer for sure.
So I already protect against like private IPs and look back IPs, or like a loop back IPs. So you can only actually fetch external IPs, and then it's actually served from like an external micropayment server. So I was also going to change it so that did the parsing rather than your local machine, which seemed like a lot safer. But again, I had to stop at some point, so I stopped. So yeah, check it out. Let me know what you think. If you have any suggestions, I'm all ears. If you want to learn more, you can check out my the video I posted about it. So cool.
I think there was one question on: is this going to be in the HyperSDK DevNet?
Yeah, this is the way that you will interact with the HyperSDK DevNet, is with this application. So it will showcase the transactions like the TPS and stuff like that. And then you will use this sort of wallet experience rather than using a CLI or something. In the future, we'll integrate it with like Core and different things like that. But for now, I really, because it's still in rapid development, didn't want to bring in other teams yet to like be sucked down that rabbit hole of random changes. So this is a really nice way to have a lot of flexibility with what we're building without really blocking anybody else. So yep.
Cool.
Sweet. Yeah, so I think that's it. We had one more topic where we wanted to talk about fees, but we're pretty far over now. So we're going to move that discussion to next week. So if we can wrap it up here.
Awesome. I think we're good to go.
Yep, we can call it now.